Oh no.
How was your
Not
weekend?
this again. It was great. How about you?
It was nice. Very relaxing.
Brother. Yeah, that's all it is. Just slipping out. Okay, so the exam is Friday. Exam 3. The review materials are up. So it starts.
Is there 4 exams in the final or 3?
3 in the final. This is exam 3. Okay, I think we should be good now. All right. So yeah, start studying soon, especially like if things didn't go as well as you'd hoped on 1 and 2, that the difference is being better prepared for the exam. So you got to start studying early and then get your questions answered. Have the conversations with other students and me to make sure you really understand it before the exam, not reviewing the exam after you took it. Okay, so like I said, I put some review materials up, and I will continue to update that. The thing on Canvas. Let's see if I can find that. Hello. There it is. Okay, so you go to modules. It's the very first thing. So, and then the videos are organized by exam content. And actually, it starts with double integrals. So optimization is not on there. So double integrals, changing the order, polar double integrals, everything to do with triple integrals, cylindrical coordinates, spherical coordinates, and then what we do this week, which is we're starting vector fields. All right, so if you go to Exam 3 Study Resources, you'll see a couple practice. So there's a concept and skills outline. That's comprehensive. Everything on the exam comes from that. A couple practice sheets, practice A and practice B. What's on the cover page? I think, let's see, is there some formulas I give you? Yeah. Oh, so then I'll have you fill this out for a bonus point. Tell me what X and Y and Z are in cylindrical coordinates and spherical coordinates. So we just fill that out before you start, and then just notice all the, and then also label not only put those in, but then label this generic diagram of an arbitrary point X, Y, Z. So you're gonna label, label the diagram, fill in the table, and that will be your kind of your formula sheet for the exam.
What is that extra credit?
1 point. I mean, it's stuff you have to know anyway, but I'm just putting it on, you filled in on the front sheet. All right. Notice I've got there's a couple on the practice sets, practice A and B, there's a couple notes here. So something you can ignore and some extra information about one of the problems. So read these carefully regarding sets A and B. And then I'll give you solutions to the written homework. Oh, so the written homework for this week, do you prefer it do Wednesday night so I can post solutions? You have all day Thursday to review solutions, or do you just prefer to have more time and have it due Thursday night before the exam? Do you want to make it Thursday at 5 p.m.? So then you have Thursday evening to review the solutions? Is that a good compromise? Okay, I see some nods. Thursday. I'll push it back to right now. I think it's Wednesday at midnight, so that homework will be due Thursday at 5 p.m. and then that's when all the solutions will be posted. Other questions? Okay, let's get started. So we were talking about vector fields. We introduced vector fields last week, so let's just review the idea. A vector field is the idea that every what in a coordinate system has a what associated with it. So a vector field is a mapping from what to what. So where's my pen? My pen is gone. Where's my pen? So, okay. Every what in a coordinate system has a what associated with it. That's what a vector field is. So every point, location, has a vector associated with it. That's a vector field. Okay, so the components of the vector are determined by the location. So each component is a multivariable function. Each component of the vector is a multivariable function where the variables are the coordinates. So this is an R2 vector field. So the x component is determined by location x and y as a multivariable function. The y component of the vector also determined by location x and y. And that makes a vector for every location. And then similarly, that's an R3 vector field, right? Every point in space has a three-dimensional vector associated with it. Okay, so that's the idea. So let's practice. I don't have. I think it's called. Okay, so we did this one. Let's go on to number 3 here. All right, so I'm gonna give you different locations. You're going to figure out what this vector field is. So this is the point x. This is our x coordinate 1. So this is the point 0, 1. This is the point 0, 1. And so I'm gonna give you different locations, and then so you need to come up with this, so you're going to have to do some writing here. So this is the point 0, 1. Everyone got it? Okay. Next point is -1, 2. All right, so that's this point here, -1, 2. Okay, -2. Here's, oh, sorry, 2. This is 2, -2. Here's -2, 0. Let's give another one here. How about, and then how about 1, -1? Let's do 1, -1. And here's 1, -1. So now your task is to figure out what this vector field is. Can you write the formula for this vector field? Do you want me to show one of these again? If you want me to show, I can show one of these again if you want. Which one?
You showed the first one.
0, 1? There's 0, 1. Yeah.
You showed 2, -2.
2, -2, sure. There's 2, -2. Did you figure it out? So you weren't tracking with me when we were doing it. Another repeat of any of these? Okay, so a reminder, we're out of the back 3 rows from here on out. So no one, don't move now, but starting Wednesday, no one in the back 3 rows. There it is.
I got the x coordinate or the x vector, but the y.
You're able to get the x coordinate. So what do you think the x coordinate is?
X plus 1.
X + 1. People are nodding. So the x coordinate of the vector is always 1 greater than the x coordinate of the position. Anyone come up with the y coordinate? Yeah, Connor? X minus y. X minus y. All right, so that's this vector function, x plus 1. Let's see. Where is it? Anyway, yeah, that's right. Oh, I must have done something else. Okay, anyway. Yep, x plus 1, x minus y is these are the functions that determine the coordinates of the components of your vectors, right? Based on the coordinates of the point. So if you put all those, if you kind of show, so this is the whole, shows the whole thing. Okay, but now, so the vectors are now like to scale relative to each other, but they're not the actual size of the vectors, but they're to scale relative to each other. So this is the vector field x plus 1, x minus y. What would we see if we showed all the vectors? What would you see? When you
every point has a vector, so even the points that aren't on the graph,
yeah.
you'll see like blue screen.
Yeah, so exactly. So all you would see is just blue. If I showed every vector, it would just be all blue. So in order to see the idea of a vector field, you don't show every vector. You just show a grid of them, so you can see what's actually happening. But if you were to show, if you were to show every vector, all you would see is just a big blue square. All right, because there's a vector for every point, right? There's a vector for every point in the plane. Let's see if we got another one here. Yeah, that's what you would see. All right, so here's another vector field. So let's what's the purpose of these, or so what's the application of these? So there's lots of applications of these. Here's the Gulf Stream, right, around Florida, the Gulf of Mexico, Atlantic Ocean. So what every vector is showing direction and magnitude of current. Direction and magnitude of current. So if you kind of connect, if you connect vectors like they're doing with these white, kind of these white strips here, there's what's called flow lines, right? So if you set something in the water, it would flow along the flow lines. And then the magnitude of the vectors is determining the magnitude, in this case, of like velocity of flow. And direction, of course, is the direction of flow. Here's a similar, this is the English Channel, right? So this is the velocity, fluid velocity in the English Channel. Where's my, oh, what happened? Oh, here we go. So here is, this is a wind field, right? So this is showing wind vectors. Notice Arizona in July. Right there. Very hot. No breeze to cool us off. Okay, 0 vectors. Okay, so this is another idea of a vector field, wind field. Another one is a magnetic field. So here's a magnetic field. So this is like you've got repulsive forces here at the one end of the dipole, and then attractive forces here. So you're seeing the magnetic pull at any given point around this thing, right? It's creating a magnetic field. And so you've got attraction on the left end, you've got repulsion on the right end, and then all the different vectors, magnetic forces around that thing. Okay, so that's another example of a vector field. Here's an electric field. I've got 3 charges. So I got a red and a black here, right? So you have a red there. So would that be positive or negative? Positive? Red positive usually? Red's negative? I can never remember. Red, yeah, okay, red is usually positive, okay? So, which would make sense because electrons would be attracted to the positive. All right, so you got positive, and then a positive and a negative almost on top of each other there. And so as a result of putting those 3 charges, you have the, these are really the flow lines based on the electric field. Because you're not going to curve, right? Your vectors aren't going to curve. But you put the vectors together and you get flow lines that are curved. Okay, so those are some examples. So what next? All right, some more practice. So I've got I'm just going to show you the whole field, and you have to, again, you're going to have to come up with what the field is for all these. One more. 1, 2, 3, I need number 2. There it is. Okay, so you're working together on these. Oh, and so each of the components of x and y are either plus or minus x, plus or minus y, plus or minus 1 or 0. So those are your choices for every component. Choices are plus or minus x, plus or minus y, plus or minus 1, and 0. So for instance, a vector field might be minus y 0, or x negative x, or 1 negative y, or something like that. So you're for these four, you're coming up with what they are using those 7 possibilities for your x component and your y component. Okay.
Kind of.
So what do you mean by slope field? What do you
It's like the same like type, like it looks like a slope field, right? Except for it was slope field in the direction it has the slope instead of the.
Okay, hold that thought. Hold that thought. All right, Lily, did you get this first one? What do you think? X 0. Can you kind of explain how you came up with that?
I saw that the vectors the exponent of the vectors were increasing as x increased.
Right, good, okay.
And then I saw that like they were all flat and there's no y component to any of them.
Good.
So I had to be zero.
Yeah, good. Yep, so the x, it's always whatever your x coordinate is, that's what the x magnitude of the vector is. Positive getting more and positive going right, negative getting more negative going left, and then no y component, so x 0. Okay? Good, okay. Let's see here. I got something pinkish, violet, okay. So here we go, this one. Cooper, did you get this one?
I said 1x.
1x. And I see some nods. Okay, good. So why 1x?
All the vectors have the same x component.
Just yeah, constant to the right. Okay.
And then when x is greater than 0, the y component is positive.
X is greater than 0. The y components are positive. Okay.
And then when it's less than 0, it's negative.
Yeah. So as you go further to the right, your y is growing more and more positive. So that would mean it's x, right? And as you go more and more to the left, your y components get more and more negative. So that would indicate 1x. All right. Zach back there, did you get this third one?
I got that the first component is y. I didn't get
The first component is what? Y? X component is y? So that would mean that, let's see. So how did you come up with that?
I came up with that because I noticed that as the y increased, it started to move more in the x direction. Like it's a larger x.
Right, so like looking for any x value as y increases, you're getting a larger and larger x component. As y decreases, you're getting a more and more negative x component. So that'd be y. And then what about the y components here? So what's happening to the y component? Are they getting larger positive going this way and larger negative going this way? Is that right? So it would be x, just yx. Finally, last one. Brian, did you get it?
I said negative x, negative y.
Negative x, negative y. Agree? As you go to the right, your x component is getting more and more negative. And if you go to the left, you get more and more positive. That's the opposite of x. And there's the same thing going up and down. All right, any questions about any of these? Does this make sense? Please ask, because now we're going to do 3D.
The y comma x.
Y comma x? Just in the whole thing?
That hurt my eyes. to
Okay.
look at.
Yeah. It's, so look, as x increases, the y components of the vectors are getting more and more positive, and as x decreases, the y components are getting more and more negative. So that would indicate that the y component is the x coordinate. Yeah, and then if you go in this direction, so if you go in the positive y direction, your x component is increasing. And if you go down, your x component is getting more negative. So that would indicate that the x component of the vectors is y. Yeah, that's the hardest one. Number 3 is the hardest one, probably. Yes, practice. Practice. All right, so let's do that. Let's practice here. Okay, here's the first one. Okay, so what happens is if it's closer to you, the color is more vibrant and saturated, and as it farther away, it kind of grays out. Does that make sense? So that helps. And I'll keep moving it, okay? So the ones that are closest, the most positive X, have the deepest, the most vibrant blue, and then in the negative X direction, getting more gray. So I'll give you some different views here, okay? So there's the YZ plane. That's looking at the YZ plane.
It's the same options, right? Yeah. Does it go away? Oh, what? He's sick. I knew there was a curvature.
So this is looking, X is to the right now and Z is up. X is to the right and Z is up. X is to the right and Z is up right now. X is to the right and Z is up and Y is into the screen. I can come back. So let's try XY plane. There's XY plane. X is to the right, Y is up now, and Z is coming at you. Okay, so there's the XY plane. There's XZ. So this is closest, and that's farthest behind. So just from closest to furthest away. And this is X and Z. And then here is YZ, looking in the YZ direction, down the x-axis. Okay, I think you got it? Top down again? Top down view. Oops, sorry. Didn't know I was still holding on to it. This is top down.
This is almost as stressful as solving the Rubik's Cube. Yeah, it's water. Negative, right? It's water negative.
Why? It's going up just
Yeah, yeah.
then the y component is just lower. Yeah, no, because the y component is staying the same.
Oh, so And there's a bunch more layers to see if you make it.
Okay, Alexandra, you think you got it? She wants y10. Z component? Looks pretty zero-ish. Good job. Next one. Here we go. This is XY. Stop. YZ. Y to the right, Z up.
That's true.
And then here's YZ coming here. Okay, let's see. Jose, did you get this one? Any of it? Y equals 0. Okay, that's a start. What about Z? So this is the YZ plane. So you want Y to equal 0. What about Z? What's happening to the Z components of these vectors? What's that? Equals Y? So how does the Z component increase as you go this way? That would be Z equals Y, right? That your Z component would increase as you went in the Y direction. But what's happening? Z component is increasing. Okay. So what's happening is Z components of the vectors are increasing as Z increases, right? And Z components getting more negative as Z gets more negative. So they're really just mimicking Z, right? Do you see that? So the Z components and the Z coordinates are the same. What about X? It won't move, and then when you do that, it's like crazy. All right, what about X? So the X components of the vectors are kind of like always the same positive value. Do you see that? The X components. This is X to the right now and Z up. So you're always going the same amount in the X direction on each vector. So 1. So 1, 0, Z. 0, Z. Okay, so if you want to, we can do one more after class if you want to stick around and do one more harder one after class. We got to move on. Here we go. So there's another dipole vector field. All right, so let's recall the gradient. Remember the gradient? What was the gradient?
It's like a
So I want you to find the gradient of this function, x squared plus y squared minus 3 at -1, 2. At -1, 2. And explain what the gradient means. Remember the gradient? Okay. So yeah, so 2x partial with respect to x is partial with respect to y is And so the gradient at negative 1, 2, you said is? Okay, and what did that have to do with the function? What does the vector negative 2, 4 have to do with the function? Yeah, Michael?
Is that the direction you would have to go to encounter the max change in f of x and y?
He says it's the direction you have to go to encounter the max change of z, the function f, at the point negative 1, 2.
Like along the surface.
On the surface, right? Yep. So if you're on the surface f at negative 1, 2, you would have to go in that direction, and it would be the direction of max rate of change. And what would the rate of change be? Remember? Yeah. So this is direction, and the magnitude would be what, root 20? So your rate of change would be root 20 in the direction of negative 2, 4. Okay? So that's review. So now, so what about at any xy? What would be the gradient at any point xy, not just negative 1, 2? What would be the gradient at any point xy? 2x, 2y? Notice anything? That's a vector field, right? The gradient is a vector field. So it's a vector field that shows what? The vector field that shows what? Yeah, it gives all that vector field gives all the information about the rate of change of the surface. It gives the direction of max rate of change at any point and magnitude. So a gradient field. So the gradient is a vector field, so we call it a gradient field. It's the vector field partial respect to x, partial respect to y. Indicates the direction of greatest rate of change. And its magnitude is the value of that greatest rate of change at any given point xy.
The greatest rate of change is just occurs on the cylinder.
What's that?
So the greatest rate of change just occurs on the cylinder, like if you go in the direction of the cylinder.
It's not a cylinder though. This is you know what is this?
The surface, right? But then it's a circle and this just down through units, so wouldn't the z's just go? Oh wait, no, z is that.
This is z equals x squared plus y squared. So let's look at an example here. We'll look in 3D. We'll talk about this. Yes, right. All right, so sketch the surface to find the gradient field. We already did that. And then you're going to sketch the gradient field. So sketch the surface, sketch the gradient field, and then explain how those two things are consistent. Sketch the surface. We've got the gradient field. Sketch the gradient field in R2 and explain how the gradient field is consistent with the surface. The vector field 2x, 2y. Yeah, Cody.
Every vector is just double, like the standard, it's like a standard vector field x, y.
Okay.
You just take all of the vectors and double their length.
Okay, well, what's that? What's the vector field xy? So what is it like?
Well, it's
The vector field,
explosion outwards, I suppose.
like an explosion outward, he's saying. So all the vectors point
Away from
right, exactly away from the origin. And then the further away you are from the origin, what about those vectors? They get bigger and bigger, right? So something like that. So I'm showing it in the xy plane. Okay, what about this surface, x squared plus y squared minus 3? What's that like? What is that? What kind of surface is that? Circular paraboloid opening up. So how are these? Let's see. I'll try too dark. Try gold. Not bad. So how is the surface consistent with the gradient field? How is the surface consistent with the gradient field? Both talking about both the magnitude and the direction of the vectors.
If you think of it like
Go ahead.
like z planes, like z projection, it's exponentially getting wider. So like the circles that make the shape, it's not like a cone. So the further up you get, the further away you are from the origin. So the greater the rate of change in z is.
Okay, so the further you're away from the origin, the rate of change is greater, right? So because the surface gets steeper and steeper as you move out away from the origin, and so that's shown in the vector field how? Vectors get bigger away from the origin. And then what else? What is the direction of max rate of change on this thing?
Directly outward from the origin.
Yeah, so your max rate of change is always going to be in the direction directly out from the origin. And then, so then at 0, 0, you have like 0 rate of change. So your vector is, or down at around the vertex there, you have a much smaller rate of change, but pointing out from the origin. So you have small vectors pointing out from the origin. Do you see how the vector field is the gradient field is consistent with the surface? Okay. So I think I made nice homework to at 5. Is that right? Okay. So, and then I'll take a look. Just watch web work for when the next one will be due. Probably Wednesday at 5 if it's doable. But just watch Canvas and web work and start studying tonight. Start studying for the test Friday.